Is going to give us a talk about the transforms course he's going to be teaching next semester. So without any further ado, I guess I'll turn it over to Dr. Azoff.
Okay. Well, thank you. I guess actually the main thing that I want to do today is convince you that you've been using transforms all your life, at least your mathematical life. And one thing that I've always wanted to do, when I've been to other talks and stuff, sometimes people do this. They actually look up a word in the dictionary and tell you what it means. See if, so you got to use alphabetical order for that is the only trouble. All right. Okay, all right. Yes, here it is. Oh, there's transformation. Okay, transform. To change the shape or appearance of, convert or change the character of, transmute. Of course, you don't know what transform means. You're not. Metamorphose, change the form of an algebraic equation. That's pretty good for a dictionary. Into another of different form without altering its value, whatever that means. Okay, so anyway, the idea of it is that what a transform really is, it changes things, and what we call that in mathematics is a function. So a transform is a function. The difference is that it's functions that you're used to seeing, used to thinking of functions, let's say, from R to R or something, but transforms usually often are functions from a big space, a vector space, maybe a space of functions itself, into another space. And they are used, as the definition said, sort of to try to transform or change one problem into an easier problem. Okay, now here's an example that you've been using, since kindergarten or whatever. If you want to solve the equation x plus 7 equals 5, you perform a transformation of adding -7 to both sides of the equation, and that transforms the equation to one whose solution you know. All right, that's the first example. That's it. No. Another example is the quadratic formula, which you all, I'm sure, know and love. So let's assume the leading coefficient is 1. So let's say it's x squared plus bx plus c equals 0. And what we usually do to solve that is to complete the square. So it'll be x squared plus bx plus b over 2 quantity squared plus c equals 0. And then we're going to make another way of thinking. Okay, that's all right. All right, well, I think I would have caught it later, maybe. Is that okay? All right, so now the other, okay, so this could also be written as x plus b over 2 quantity squared equals squared over 4. It'd be bad if I get this one wrong. And then, doing a transformation is also like applying a function as a way to think about it, or changing variables. So what we really are sort of doing here is making a change of variables and letting y equals x plus b over 2, and then we get the equation y squared equals b squared over 4 minus 4c, I guess, if you want to write it that way. And, okay, this is a simpler equation, right? It's just a question of finding a square root. And this is our first example of showing that it's much better to work in the complex numbers. If you're working in the real numbers, this equation maybe wasn't b to the 4th, right? b squared. How come you didn't catch that? All right, so this equation is in the real numbers. It might not have a solution, and it's bad not to have solutions. So I hope you believe that. So we work it in the complex numbers, okay, and then we solve this equation because it's an easier equation, and then we do the inverse transform. Since y, the way we get y from x is by adding b over 2, we just subtract b over 2 and we get the solution. Okay, so those are two examples from, I guess that's kindergarten, maybe that's like your first year of high school. Okay, what is the transformation that you C all know and love from differential calculus. I mean, don't think too hard. The derivative, right? So basically what now, it doesn't have all of the nice properties of transformations. One of the nice properties of, say, this transformation and most of the other ones that we're going to talk about is that they're invertible. You can go either forwards or backwards. Well, differentiation isn't quite reversible. So the transformation, so we could talk about like D for all differentiable functions. And then, well, let's say continuously differentiable so that we don't get into too much trouble. And then the differentiation operator, D, goes from D to the set of all continuous functions, let's say on some interval, by, reasonably enough, the function is f prime. Now, basically, what we do in calculus, I'm sure you all know that, is that we learn information about the original function from the transformed function, right? So we learn from the transformed function when the original function is increasing. We learn when it's decreasing. We learn when it has relative extrema, right? So that's an example of a transform in calculus. Okay, so the next one, I want to talk a little bit about power series. And think of that as in the guise of a transform. So we'll just talk about power series, let's say, centered at the origin. So what is a power series? So power series, I hate this, but I'm not going to, I know that you'll hate it more if I actually do the formal, a really formal definition. It's an expression of the form, whatever that means, an x to the n, that's called the power series. And basically what happens is that this converges for some x's. You can plug some x's in, and for some x's it will converge, and for other x's it will diverge. And not for others. Well, maybe. Okay, now as a matter of fact, you can say exactly which x's this does converge for. So those of you who had 3100 or maybe 4100 could tell me what that is. So basically, so what happens is that we say that there's a number called the radius of convergence. R called the radius of convergence. Of the series, such that the series does converge converges for absolute x less than r, and it diverges for absolute x greater than r. All right, and then for absolute x equals r, sometimes it converges, sometimes it doesn't. That's a more delicate question. Anybody know any characterizations of what this r is and any special cases? So basically, it's sort of an application. Finding r is like an application of the ratio test. It gives you one condition. Another, a fancier condition is like of the root test. If you cover that, maybe in your stereo manual, most people don't. But what does the root test tell you? I mean, okay, we better not say that. The ratio test, right? So the ratio test tells you what r is in a very special case, right? It tells you that that if the limit of the successive coefficients exists, all right, then let's see if I do this right. Let's see. I guess we want it the other way around. Okay. Then the radius is this limit. Well, then R is the absolute value.
No, the limit might not exist without the absolute value.
Well, okay, but it was a true statement, just weak. Weak but true, right? I'm only going for the minimum here. Okay, then this R is the radius of convergence. Okay, so what would an example be if we take the series 1 over n factorial x to the n equals 0 to infinity. So then when we look at, you sure I did this right here? A sub n, is R is it? Okay, I don't know. All right, let's see. Oh yeah, I don't know. Okay, well let's just see. The 1 over, yeah, a. What should I have done it? Okay, let's just see. 1 over n factorial over 1 over, I don't think I did it right? It's the reciprocal, isn't it?
No, it's right.
I don't know. This goes in the numerator. Oh, yeah, that's right. Okay, all right. All right, well, it'll only get better. Okay, let's see. Hopefully, right? N plus 1. And that goes to infinity, right, as n gets large. So, in fact, the radius of convergence of this series is infinity. In other words, this series converges for all x. Okay, now if you didn't know, okay, now here's a fact about series which you may or may not have proved, probably didn't in your course, is that within the domain of convergence, so by the way, this is the radius of convergence and this set here, well, so within the radius of convergence, you can actually differentiate power series term by term. So you can, so here's a fact. Power series can be differentiated term by term. That is to say, we're out. So in this case, if we do this, let's look at this power series. I guess, yeah, are you looking at it? Okay, so if we do the derivative of that power series, so that represents a certain function. And if we differentiate it term by term, so, well, the constant term goes away. This is the sum from n equals 1 to infinity of n, x to the n minus 1 over n factorial. But you can cancel the n with the n in the n factorial. And this is the same as the series n equals 1 to infinity of x to the n minus 1 over n minus 1 factorial. And you can just do a change of variables, right? And so this, in fact, is the same as the sum from n equals 0 to infinity of x to the n over n factorial. So in other words, if we had never heard of any function whose derivative was itself, right? If we just know that power series we know that this power series converges everywhere, and its derivative is equal to itself. Actually, let me just give this function a name here. So the two properties that what we just proved about f is that f prime is equal to f, and the other property of f is that f of 0 is equal to 1. And if you remember one of the existence and uniqueness theorems from differential equations, this completely determines f. So it's perfectly possible to just show, so we could define the exponential, this function, this way. And actually, if you're unlucky enough to take 2400, what do we do for erasers here? Okay. that actually would happen. So we can actually make the definition of the exponential function that way. So we can define x of x, or e to the x, just to be this power series. And I'm going to spare you that stuff, but you can, using this, you can get all the properties of the exponential function. You can get that the exponential of x plus y is exponential of x times exponential of y, and all the good properties. And so, in fact, and because this function goes to infinity, there is a particular number, a unique number. So this, there's a unique number such that the exponential function is, well, e of 1. Let's just put this, define e to be the exponential of 1. And so then, in fact, what exponential of x is, because of the multiplicative property, is that x of x really is e to the x. The advantage of doing it this way is when you do it, you know, if you remember from your calculus course or whatever, they assume all these things about the exponential function without proving them. Here, you know, well, we assumed it without proving it too about the series, but otherwise, you know, it came through pretty easily, right? Okay, again, it makes perfectly good sense to, I said, you know, it's sort of useful to extend this, and there's no problem with it because this converges for all x. If we put a complex number z in, we still, the radius of convergence still works out the same. We'd still get like an infinite radius of convergence. So this will actually, so we can actually define, so, well, I mean, I could just say this. We originally defined it for x and r, but we could, in fact, define e to the z to be the sum from n equals 0 to infinity e to the n over n factorial for any complex number. That makes perfectly good sense. So if we do that, actually, we can sort of see Eulers formula. Okay, yeah, I guess the other thing, yeah, so we can see Eulers formula from this, for example. Let's do the series for x of I. I can just write the regular thing, x of ix. So according to this definition here, it's the sum from n equals 0 to infinity of ix to the n over n factorial. Well, we can have the even terms, which will be the sum from n equals 0 to infinity, or let me write k equals 0 to infinity of minus 1 to the k times x to the 2k over 2k factorial. So all the even powers, right, don't involve I, so we can just gather them together, plus then we get I here, and we get all the odd terms, which is sum from k equals 0 to infinity of minus 1 to the k, x to the 2k plus 1 over 2k plus 1 factorial. And actually, I won't subject you to that if you haven't seen it before. Oh, I'm sure you guys have seen it even in calculus. What is this the series for? That's cosine of x. And then this is sine of x. Okay, so there's Euler's formula, right, relating the exponential function to the trig functions. So basically what it means is that there's only one transcendental function, right? I mean, if you understand the exponential function, if you know, you can, so we can actually recover the trig functions from the exponential function. So the way to do that is if you do cosine of x plus cosine of minus x, or let's start again. If we do e to the x plus e to the minus x, let's see, ix, e to the minus ix over 2. All right, if you just see what happens when you plug in minus ix for ix, and you add them together, all the odd terms, right, go away. So this is just cosine of x, and you can recover the sine function. This way. All right, so that's an example of one thing that you can do with these series, right, is you can actually use them. Now, you can actually solve differential equations with these series. I won't subject you to that, and we'll just talk about. So you could actually think about, suppose we didn't know, suppose we weren't so smart. I'm sure not a good assumption in your case. But let's say we were trying to find the cosine function or something. So let's say we didn't know what it was, but we just knew the differential equation that it satisfied. Let's say it's y double prime plus y equals 0. And we would want y of 0 to be 1 and y prime of 0 to be 0. Right? That's what we want the cosine function to be. So what we could do is we could just try y equals a series like this. And then we could substitute, right? We could find y double prime, and we could substitute, gives us recursive relations on the a sub n's, right? And then we can find all the a sub n. Anybody want to do that or not? You've probably done it before, huh? Okay, so we can actually, all right, here, I'll just do this much of it. So this would be from sum n equals 2 to infinity of n minus 1, x to the n minus 2. So we'll just say match and solve. Right? And you would actually get that the coefficients, the a sub n's, would actually be the a sub n's that work for the cosine function. So now we could have done one where the recursive relations are terrible, but we're not going to do that, right? But you can solve a lot of differential equations that way. That's called the power series method, right, of solving differential equations. Okay, okay. Now I want to sort of think of this as a transform problem. I want to think of power series as really a transform problem, and this is the way you can think of it. We'll have two spaces. We'll have, let's say, seq, which is all sequences, reasonable sequences. I'm not going to define that, but it means they don't grow too fast. Of complex numbers. And then we'll define, let's say, I don't know, analytic. Okay, to be a certain class of nice function. Won't say what that is yet. Well, actually, I can tell you what it is. So they're the functions which, all right, let's just say analytic functions, nice functions. Well, we could have entire, right? All right, yeah, let me just do that. Say entire functions, ENT. So this is all those functions from the complex plane to the complex plane, which are differentiable everywhere. And we have a map, let's call it S, that goes from the sequences into the entire functions. Well, okay, from at least, I didn't say what they were, reasonable ones, right? Goes from the sequences to entire functions by what? I basically start with this sequence and I use that as the coefficients for my power series, right? So by S of some sequence, A sub n, is just the series from n equals 0 to infinity of A sub n x to the n. Now this map actually has a partial inverse. Let me call that T for, what do you think T stands for? Well, that would be safe, but actually starting with entire functions and giving you a sequence. And how can we do that? So basically it's supposed to like go backwards, right? So it's supposed to tell you, starting with the function, what the a sub n's are, right? So, well, let's just do it one at a time. If I have this function, sum n equals 0 to infinity of a sub n, x to the n, and I evaluate that at 0, that's just going to be a sub 0, right? Because all the rest of them. So in other words, if this is your function f, so then you can recover the first, I guess, a sub 0. All right. How about the other, how do you get like f of 1? How do you get a sub 1? Well, we know that we can differentiate term by term. When we do, well, of course, the a sub 0 is going to go away. All the higher powers other than x, right, are going to still result in 0 when we plug in. So we're just going to get f prime of 0. And somebody want to tell me, in general, what a sub n is? If you remember it from... Okay, so it's the nth derivative, right, of add 0, right, all over n factorial, right? So, so in other words, what this map T is, and now you can tell me what T stands for maybe. So T starts with the function, and it gives you the sequence f of 0, f prime of 0 over 1 factorial. All right. Taylor, right, stands for Taylor's theorem. So Taylor's theorem is really sort of telling you that, well, that this map is at least partially invertible, that nice functions actually come from power series. And what we were doing, I didn't want to tell you before because then it wouldn't have made any sense, but really what we're doing when we're like sort of solving, trying to find whose derivative is itself, right? What we're doing is we're transforming the problem from the function space into the sequence space, right? So we sort of like replace the function with its sequence of coefficients. We know, what we want in the derivative. We know what we want the sequence of coefficients to be. And so then we can solve recursively and find out what the coefficients are. Right? So that's really what we're doing. So that's a typical sort of application of transform, is you're trying to solve a problem in one space. I mean, it might seem sort of silly here, and you transform it to a problem in another space, right, where it's easier, right? So it's just, yeah.
Are we always going to be able to do that?
Well,
be able to go from a function to a...
Well, that's why I told you. I mean, this is a big theorem in complex variables. This is called an entire function's called entire if it's differentiable everywhere.
Okay.
And it turns out that if you have a function which is complex, this is the big mystery that you'll learn when you take one of the big mysteries in complex variables. If you take it, is that if a function is complex differentiable, I mean, just the same definition of derivative that you use in the real case in some open ball, okay, then automatically this Taylor series here converges in that ball. So the Taylor series always converges in the biggest ball where the function's analytic. All right? And so in other words, and that's basically going to happen, in the ball. I mean, you can actually sort of determine it, right, by looking at all the coefficients here, because that allows you to recover the a sub n's. And from the a sub n's, you can take the limit and figure out what the radius of convergence is. But that's sort of like backwards. The main thing is, if you know the function, you know where it's differentiable, you know where the biggest ball is that you can expand it in. All right?
All right. So
that's about power series. The next couple examples, or the next section of the talk I want to tell you about. So this is supposed to convince you that you use transforms in calculus, you use transforms in sequences and series, although you didn't know it, and or at least you could have. And the next thing I want to tell you is that we use transforms in linear algebra. I don't know what number I'm up to, 4 or 5. So in linear algebra, okay, and so here's a problem. And my apologies to Hank. He asked me to tell a joke today that he hadn't heard before. But of course, I'm only going to tell the one joke that I always tell. So, okay, so this is the problem that we want to talk about. We want to transform it. We'll make it a concrete problem. So it's to find all powers of a specific matrix. Let's say of the matrix 1/2, 1/2, 2/3, 1/3. All right. So the thing is, what matrices is it? You know it's coming, right? All right. So I have to tell you the joke first of all. Okay. Anybody not heard it yet? The salmon joke? All right. You've all heard it? Okay. All right. What's green, hangs on the wall, and has 4 wheels? You can guess from the name of the joke. It's a salmon. Okay. You have any objections?
Salmon aren't green.
Well, you could paint it green. Another objection?
Salmon don't have wheels.
That's the third one.
Oh.
Okay. So,
It's not like you've taken a class.
all right.
Do salmons hang on the wall?
You can hang it on the wall.
Salmon don't have wheels.
Yeah, what about the wheels? I just threw that in to make it challenging. So that's the way, I make up my tests and stuff, like that. All right, so now I can tell you what it has to do with this problem. Are there any matrices that it's easy to find powers of? The identity matrix. All right, we're not going to be able to make this the identity matrix. Diagonal matrices. Oh, but this matrix isn't diagonal.
Let's make it diagonal.
We'll make it diagonal, right? So here's what we're going to try to do. We want to make it diagonal. We're going to look for a matrix P. Find a matrix P. All right, such that, and so that's going to be an invertible matrix P. This is what we want to do. And a diagonal matrix, for some reason they write this capital gamma, and a diagonal matrix. We could use D, but we've used D up too much already. Diagonal matrix, let's say lambda. Okay, so let me tell you what we want, such that, well, maybe you guys know, such that if we do A times P, it's the same as P times lambda. Let's see what that means and why it's good and how we get it, right? Okay, so let's write P as, it's got like 2 columns in it, right? So maybe we'd write it as, the first column we'll call X and the second column we'll call Y. And on this side of the equation we got the column X and the column Y. And then we're multiplying by this diagonal matrix, let's call it little lambda, little mu. Okay, now what happens when you multiply a matrix? Yeah, how do you multiply matrices? That's one thing that you're supposed to know before the transforms course. You basically do it 1 column at a time, right? So this left-hand side of the equation here is AX for the first column, and then AY for the second column. And now, how do you multiply a matrix by a diagonal matrix on the right? You can do it, and you can...
That's easier. You just sort of like take each column and multiply it by each of the...
That's right. So it's going to be lambda x here, and it's going to be lambda y here, right? So basically, this is what we want, right? And that's the same thing as saying what? Maybe it's mu. We don't want that. Okay, that's the same thing as saying what? It means that AX equals lambda x, right? And AY is equal to mu, I'll get it right this time, times y, right? So these things have names, right? X is called a vector x. Of course, we don't want x and y to be 0. That would be, my class would certainly give me those answers right away. And why? Okay? So the question, this is a hard equation. Why is this a hard equation? because there's two unknowns in it, right? There's the scalar, lambda, which is unknown, right? And the vector, x, which is unknown. And that's sort of hard. I mean, if we knew what lambda was, well, let's put it this way. First of all, if we knew what x was, it would be pretty easy to figure out what lambda is, right? There's only one lambda that could work. On the other hand, if we knew what lambda was, we could find x. So given lambda, well, let's just put it this way. Lambda works for some x if and only if a minus lambda times the identity times x is equal to 0 for some non-zero x, right? All right, so now is there another condition for which you know when that happens? When is, in other words, it's saying that the null space of a minus lambda I is non-trivial, right? And do you know a condition about when that happens? Which matrices have non-trivial kernel?
Ones that are not invertible.
That's true. What's another condition equivalent to it? One that we might actually be able to use. I mean, there was nothing wrong with your, sorry. I don't know you well enough to insult you yet. But
Matrices with zero determinant.
That's right. So this is the same thing as saying that the determinant of A minus lambda times the identity is 0. I guess we better. All right, so the thing is, see, this is just an equation in one variable, right? So we could actually do it. All right, I think I'm not going to spend the time to actually do it and everything. I'll just tell you what the answer is. Lambda is 1 and mu is minus 1/6. Okay, so that's, and then I'll tell you what vectors. Now x and y, of course, are not uniquely determined. You could always use any multiple of x, but the x, one x that will work is, I believe, 4, 3. I've done this problem a few times. And one vector y, well, now that I've said that, I'm not sure that I can, is, I think it's 1 minus 1. Let's just see. If you want, we could check out. Well, actually, I used minus 1, 1, but that's okay. All right, so those work, right? And so now let's go back to our problem and see how this sort of solves it. So it's telling us, okay, what to take our matrix P for. So in other words, so we'll just take, so let's just write, we have, all right, I'll just write it. So we have A times the matrix P. We now know what that is. That's 4, 3, minus 1, 1 is equal to the matrix 4, minus 1, 3, 1. Okay, times, that's times D, which is times 1. Minus, our whole goal here, just minus 1 once would be enough, right? Our whole goal, right? You don't believe that's right?
No. Lambda mu.
Lambda mu, oh, but yeah, lambda and mu are 1 and minus 1/6. All right, thank you. Right? Okay, so, all right, so what was our goal here? Our goal was to sort of try to find A, right, so that it would be easy to find powers of it. So what do you recommend?
Multiply by the inverse.
Yeah, multiply on the right by the inverse of this matrix. So A is equal to 4 minus 1, 3, 1 times 1 minus 1/6. Do you want me to tell you what A and what the inverse is? My great record. Times the inverse of that matrix. All right, so what's good about that inverse? All right, I'll tell you what it is. Okay, it was 1/7. Let me just write it in. So it's going to be 1/7. 1/7. You can check that it works if you want, if you're bored. Minus 3/7 and 4/7, right? So that works. Okay, that's the inverse. Okay, and why is that good?
I concur. I concur.
You concur? Okay, good. I should have just let you do it. All right. So therefore, now what happens when we do a power of a? So we're going to be, say if we do a squared, we're going to be multiplying this by itself. Well, in the middle, we're going to have this times this, right? But that's the inverse, right? So all that it's going to be is just like 4 minus 1, 3, 1 times this thing squared. Well, this thing to the nth power, 1 to the n minus 1, 6 to the n. All that times this matrix, 1, 7, whatever. All right, and actually I tell you what I want to do. I want to take the limit of this, okay? So what's going to happen if we take the limit of these? All right, well okay, the matrix in the middle, this 1 minus 1, 6 to the n just goes to 0, right? So this is just going to be 4 minus 1, 3, 1 times 1, 0, 0, 0 times this inverse matrix here. And you can concur if you want. 31, okay, this turns out to be the matrix 4 sevenths, 3 sevenths, 4 sevenths, 3 sevenths. You're going to check it or not?
I don't understand entirely. Okay, so our diagonal matrix, the limit as n goes to infinity, so our mu, whatever our second term was, that ends up going to 0.
This thing here, right? Because it was like negative 1/6, right?
Okay.
All right. And so, I mean, it's just a computation if you want to, right? So you can multiply, you know, when you multiply, say, this by this matrix, you're just going to keep the first row and put zeros in the second row.
Okay.
And then when you multiply by this, you'll see that, yeah, well, let's just see what happens, right? So you got 1 7th, 1 7th, and then zeros on the bottom, right? So you've got what? Fourths, whoops.
Should be negative 3 7, 4 7.
It's all right. Just keep going.
All right. Anyway. Well, I hope it's right, you think?
Well, wait, I don't understand. You're saying that this product here ends up equaling what?
Well, that's what I was claiming. Maybe I did it.
Third matrix.
Yeah, but it doesn't matter.
It doesn't matter.
No, yeah, I agree. But
Sometimes the first column.
So here, when we do this, we're going to get 4 sevenths, and then there's going to be 0 here, right? This part here, okay, I'm going to just replace this by this second row by 0, because that's what's going to happen.
all right.
All right. Sorry, we probably ought to. Right? And then when I multiply, since the second row is 0, this junk on the bottom here is not going to make any difference at all, right?
Right.
So this is going to be 4 sevenths, right, plus 0. And this is going to be 4 sevenths plus 0. Right? Oh, where did the 3 sevenths come from?
I guess that was...
Oh, that's going to be in the second row, right? So this is going to be 3 sevenths plus 0 and 3 sevenths plus 0.
Okay.
All right. Okay. All right. I want to give you 2 applications of that. Actually, we probably ought to. Okay. All right. I'll just tell you in words because I don't want to take the time. I'll give you 2 applications of it. I'll give you a word problem. This is a very practical word problem. Let's say you have a class of 60 people. And let's say that everybody comes the first day. This part isn't maybe so realistic. And then whether you come on a succeeding day depends on whether you came the preceding day or not, okay? So if you come on day n, it implies that you have a 50-50 chance with a probability of coming on day n plus 1 is actually is going to be 1/2. So in other words, those people who come on one day, half of them come the next day and half of them don't, okay? Now this is the really unrealistic part of it, is that if they're absent on day n, then they feel guilty, okay? And they have a 2/3 probability of coming on day n plus 1, right? So probability of coming on day n+1 is 2/3. All right? So now what are some questions you could ask?
What happens at the end of the semester?
Yeah, okay, that's right. Well, so what happens after, let's ask what happens on day 0. So the first day, we'll consider that day 0. So what I'm going to do is I'm going to make a vector of those, the present number and the absent number. Okay, that's going to be my vector, let's say x sub n, is that this is on day n, right? So if I look at like x sub 0, should put some vector here or whatever, it would have been what? 60, 0. All right, now can you tell me what x sub 1 is going to be? Try to tell me in terms of a matrix like that I cleverly erased from the board. So what's going to happen on the next day? Half of those people, okay, so we have like this 60, 0 here, right? So half of the people who came the first day are going to come, the 0th day are going to come the first day, right? And 2/3 of the people who came the 0th day are going to come the first day, right? And then the absentees are just the other ones, right? Now, does this matrix look a little familiar? Okay, so that's, in other words, it's A times this vector, right? How many people come on day n? Tell me, you don't have to tell me the answer, but I mean, tell me how to compute it, or what it would be.
Can we say a to the n?
Yeah, you can say a to the n. That'll save me a little time. Times 60, 0, right? Okay, and then what question you really want to know, you said at the end of the semester or eventually, right? So really what you want to know is what's the limit as n gets large, right, of x sub n. Well, that's the limit of this a to the n, right, which is this matrix 4, 7, 4, 7, 3 sevenths, right? Okay, well, it's not going to turn out to be an integer, but, you know, you can't help it, so it's going to be 4/7 of the people who came in the class are going to be there, right? And 3/7 of the ones who were absent are, 3/7 of the class is going to be there. Now, let me ask you this question. What if we had started with nobody coming the first day?
If it were 0, 60?
Yeah. It would be the same, right? In fact, right, no matter what the distribution is on the initial day, this is the way that it's going to happen, right? This is called the Markov process, actually, where what happens on one day, what happens, the simplest, you know, when you have like a sequence of experiments, think of coming to class as an experiment. What the simplest thing is if they're independent, right? You just randomly come any day. It has nothing to do with whether you came the day before. That's the simplest situation. The next simplest situation is where what you do one day depends on what you did the preceding day, but not before that, okay? So this is actually an example of sort of an application of this diagonalizing matrices, okay, which, okay, we better, all right, I'm going to tell you another application, but we won't do it because we don't have time, is that you can solve systems of linear differential equations. Every a system of linear differential equations can be written in matrix form. If the matrix is diagonal, it's easy, right? But if the matrix is not diagonal, well, then you make it diagonal, right? Basically change variables, and then it's diagonal, and you can solve the problem. So that's another application of this. Okay, so, all right, so a matrix is called diagonalizable if, well, you can sort of guess, if it's similar to a diagonal matrix like this, which is equivalent to saying that there's a basis for eigenvectors. So I want you to tell me what's the most famous result about diagonalizable matrices that you learned in your linear algebra class?
Some people haven't learned it yet. Some people here haven't learned it yet.
Okay. Well, it's the spectral theorem. And what it says is that if a matrix, and this is, I'm going to state it in the complex situation. Have you talked about transpose yet, or adjoint? Okay, so the adjoint of a complex matrix, it's denoted A star, is just the transpose, and then you take all the complex conjugates of all the entries. So a matrix is called self-adjoint or Hermitian. There are all kinds of nice words for it. So if you have any matrix, right, which satisfies that its conjugate transpose is equal to itself, then A, in fact, is diagonalizable. And not only that, all right, so when a matrix is diagonalizable, as we've sort of seen here, it means you can find a basis of eigenvectors. Well, have you talked about orthogonality yet? Yep. Okay, so if we're in Rn, let me tell you what the dot product, in Rn, dot product is what? If you have two vectors in Rn, the dot product is just the sum of the products of the entry. Well, let's just say we're in Cn. So you don't define the dot product to just be the sum of the products like you do in Rn. But what you do is you use complex conjugates of the second vector. Anybody know why? Okay, it's because one of the useful things about dot products is that the dot product of, you want the dot product of any vector with itself to be strictly positive. Okay, it's sort of like its length, right, squared. So if we just used x1 up to xn here, or y1 up to yn here, if these were the same vector, well, we wouldn't necessarily get a positive number when these are complex. But when we use the complex conjugates, well, you know, you're going to get x1 times x1 bar, etc., right? So that is going to give you complex, right? Okay, so I think maybe we better stop with the, even though I love linear algebra, I'll tell you another result, which is going to be very important in the transforms course. There's a very special kind of matrix which is not diagonalizable, which is not self-adjoint. It's called the shift matrix. Right? And the way it looks is like this. All zeros on the diagonal, and everything is shifted one ahead. And then the last, the last thing goes back up to the first thing. So this is just everything, is just shifted around. It's like a circular, right? All right, can anybody look at this matrix and tell an eigenvalue or an eigenvector for it? So, I mean, the normal way that people find eigenvalue, or not the normal way, but the way you probably were taught, right, is like we did here, right? First find the eigenvalues, and then find the eigenvectors that go with it. A more interesting way is to do it by inspection. So can you think of some vector to multiply this matrix by to get, let's just say the vector itself. I'll give you a hint. 1 is an eigenvalue of that matrix. I'll tell you what, we better, all right, I'll just tell you. Let's just go on. All ones, right, is an eigenvector. When you multiply that, as long as we did that, right, that just becomes all ones because, well, I guess it becomes n. No, ones. All right. All right. Okay, now you can really impress me by giving me another one.
But you better tell Chris to shut up if you want to be impressed.
Well, I mean, won't any vector such that all of its coefficients are the same?
Yeah, but that's not really different.
Oh.
Okay. All right, I'll give you another one. And then, okay, then we'll move on. I have to at least tell you what the first transform is. At the very least, okay, here's the vector. 1 e to the 2 pi I over n e to the, yeah, you're supposed to get that one. Let's just make it 3 by 3. Well, that's why I was going to be impressed, okay?
Not to sound contrary, but is there a vector such that when we multiply it times that, it won't? Never mind. I retract that question. I was just kidding. Let's move on.
All right, if you say so.
It looks good.
All right, so go ahead and do that. Do the multiplication for me. That'll be your penance, okay?
Okay.
So let's see. You're going to go across the row, right, and down the vector, right? So it's going to be each.
So I have e to 2 pi I over n. Is that n there?
Yeah, but we're just doing it for 3 because we're short of time here, right?
We're only, okay.
So I'm just going to do it. I mean, you can guess. It'll be over n in general, okay?
Okay.
All right, so tell me what happens. So
we shift all the things up.
right, so this will be e to the 4 pi I over 3, e to the 6 pi I over 3, e to the, that's just 1. All right, yeah. And then this one is going to be e to the 2 pi I over 3, right? All right, so the question is, can you compare this with that?
Yes, they're different.
All right, great. So, I mean...
Yeah, I think I'm going to ask for a slightly more specific question.
Yeah, I mean, we're supposed to be finding an eigenvalue, right? So we're supposed to be finding... So is there a number? Okay, let me ask it that way. Is there a number that we can multiply this by to get that?
Yes.
What is it?
A number that we can multiply the right one to get the left one?
Yeah.
Well, I'm going to say that's e to the negative 2 pi over n.
Well, okay, if you want to, but I mean, how about just e to the 4 pi I over 3?
Again.
Oh, negative. That was what you were trying to tell me, right? No. Right? If you multiply, I mean, you just look at the first coordinate. If that one works, that's the only thing it could be, right? All right. Okay, so let's stop this. And let me tell you what Fourier analysis is about and what we're going to do in the course. So the problem for Fourier analysis is that somebody gives you a signal. So you're given, so this, I don't want to say Fourier analysis, I want to make it sound applied. So this is signal processing. Okay, so what happens is that somebody sends you a periodic function. So it could be like a musical, musical stuff that just keeps repeating or whatever. So you're given, and let's say a 2 pi periodic function. And here are the things that we want to do with it. We want to do the following things. First of all, we want to find the simplest ones. Simplest possible. And then the next thing that we want to do is, given a general input, we want to try to express it in terms of these simple ones, right? Sort of what we did in the eigenvalue and eigenvector thing. Well, I guess we didn't do that part. Anyway, so then we want to express. So actually, the hard question is, show that every vector, that every input can be expressed in terms of these simple ones. All right, and do it, right? And find the constants that work. Right? And find constants that work. All right, that is the Fourier transform. The Fourier transform, your input is the signal. And what you get out is the sequence of coefficients in the expression, right? You're trying to express it as a linear combination. It'll be an infinite linear combination, which is a little harder to talk about. Can't do it in -3 minutes. So this will go to like, well actually, yeah, -3 minutes you could spend, all right. It'll go into the sequences. All right, so that's the next thing that we want to do. And then the next part, and this is what, so that's what, so that's called signal analysis. It's sort of like breaking it up into its small pieces, okay? And then the next thing that you want to do is you want to somehow modify the output. And then go back to get another signal. So what would be an example of this? Let's say somebody sends you, right, like this musical stuff or whatever, but there's some noise in there, right? So when you compute your output here, you're going to have certain frequencies corresponding to certain pure notes, right? But then you're going to also have some jump, which is like some really small amplitude stuff, which doesn't come from the music, depending on, hopefully the noise isn't too bad, which doesn't come from the music, right, but is there. So what do you want to do? You want to filter that noise out, right? So what you do is you look at the output function here. You have some kind of, level, and you just kill all the coefficients that are level less than that, right? And then you go back, do the inverse Fourier transform, and that gives you a more pure signal. So this is the kind of thing, I mean, it's really, for the people who really do Fourier analysis are engineers, because they really, actually do this. They actually do clean up things. All right, let me just tell you the answer to these questions, and sorry for keeping you late. Won't happen again. That's my favorite line, the last day of class. All right, so I'm going to tell you what the simple functions are. So 2 pi periodic. Okay, do you know? I'll do it in the complex situation. So the nice functions are e to the 2 pi I n, where n is some integer. N equals, actually, an integer, it might actually be from -infinity to infinity. Actually, we got the 2 pi I in there already. I guess just e to the I n x is good enough, right? That has period 2 pi, right? Okay, those are the simple ones, right? Now,
It's too complex.
Sorry. I was supposed to tell the joke. All right, so those, now I'm going to just tell you this, right? When you have an inner product, you can talk about orthogonality and stuff, okay? And so there is an inner product. These functions lie, in particular, they're continuous functions, right? Let's say on the interval from 0 to 2 pi, if we want to. And we can define an inner product this way. The inner product of f and g can just be the integral of f of t times g of t, okay, bar, I guess, dt from 0 to 2 pi. Okay, that's not quite, it's not quite an inner product, because you can have a function who, if the function's continuous, let's say we stick to continuous functions, then if the inner product of it with itself is 0, the function actually is 0. So this is actually an inner product. Okay, and the nice thing about it is that in this inner product, these functions are actually mutually orthogonal. All right, so let's just check it with 1. If I do the inner product of 1, let's say of e to the I n x with 1, I'm supposed to integrate from 0 to 2 pi of e to the I n x times 1 conjugate. Right? Okay, that was a joke. All right. All right, but what is that? That's like integrating cosine. This is, let's say, for n not equal to 0, you're integrating cosine of nx, right, plus I sine of nx, but both of those are the same at the endpoints, right? So these are x. So these integrals are 0, right? So it actually means, right, that these functions are mutually orthogonal, right? So what does that solve about these problems here? It doesn't tell you that it's possible to write the function as a linear combination of these, but it does tell you, if it is possible, how to do it.
Wait, I'm sorry.
Yeah.
So we're saying that e to the I n x is orthogonal to the constant function equal to 1?
Yeah, for every n not equal to 0. They're all orthogonal to each other, in fact.
Okay.
All right? So let's say, for example, okay, so, all right, then this will just stop here. Let's say I've got some function and I want to try to express it, right, in terms of the e to the I n x. So I've got some function f of x. I want to write it as the sum from n equals minus infinity to infinity, some numbers a n times these e to the I n x here, right? And we want to find the a sub n's, right? So there's a trick, right, to make it very easy. What we do is we take the inner products of both sides of the equation with specific functions. So for example, suppose I take the inner product of this with, let's say, 1. So what happens? I'm going to get the sum of all of these, right? It's going to be the sum from n equals minus infinity to infinity of a sub n times the inner product of e to the I n x, right, with 1. But what about these inner products?
Well, we just showed it was 0.
It's 0. Is it always 0?
I'm skeptical. I find that, but yes?
Well, no. It's not 0 when n equals 0.
Okay.
So the only term that survives here is the term when n is equal to 0, right?
All right.
So basically what we get is 0 times the inner product of 1 with 1. Okay, well, that's what a sub 0 is, right? It is f of x inner product 1 with the function 1 inner product with 1. All right, if you tell me what you would do to get a sub 1, I'll let you go home. Or to the matrix or whatever you guys do. How would you get a
Derivative? I don't know.
well, yeah, that's good in a calculus class, but we're not in a calculus class. Maybe we're in a calculus classroom, but okay. I mean, why did we take, well, I told you, yeah, maybe I didn't tell you enough, right?
Ooh, how about a to the n minus 1 x? I don't know.
Well, you're pretty close, okay? I told you that actually these were all mutually orthogonal, right?
Okay.
Not only is e to the I n x orthogonal to 1, right, for n not equal to 0, but e to the I n x and e to the I m x are orthogonal as long as m is not equal to n.
Okay.
So if we want to find a1, let's just start with this equation and do something smart to it.
Like set m equal to n minus 1?
Well, okay. All right. I mean, take an inner product.
Why don't you do this?
That's all right. You know, I'm picking on you. So let's take, all right, f of x with just e to the I x, all right? All right, let's do it. I mean, because you volunteered during, okay. So that's what happens. Plus, you're the president. You know, you got to, you know, like the, huh? He's not the president?
No, I'm not the president.
Okay. Well, just like the real president, he's got to take grief, right? So it's what? E to the I, what was it? Yeah. E to the I nx with e to the I x, right? That's what we're doing. All right, what about these inner products here? Are they all 0?
No.
Which one isn't?
One when n equals 1.
The only one that's not 0 is when n equals 1, right? So this sum collapses to what? Just
a1.
a sub 1 times inner product of e to the ix with itself, right? And then what? then just divide by it, right? So then you can solve for all the coefficients. All right. If you've never seen orthonormal bases before, this is probably not the best first place. It's better to see them probably in Rn. But, huh?
They've seen them. Most of them have.
Okay. All right. Well, I'm way over, so I think I'll stop here.
Thank you, Dr. Azoff,
You're welcome.
for giving this wonderful talk. Please come and join us in the Matrix. We will have pizza and refreshments, and you can talk and get to know people who don't remember already.
Sweet.
Hey, Jacob. We're doing about 3 minutes?
What?
Yeah.
Well, sorry if it